Hello everyone, today I will present a paper survey on FairNet dynamic fairness correction without performance loss via contrastive conditional LoRA. This is for the CSIE 4536 Security and Privacy of Machine Learning course at National Taiwan University. Here is the outline of my presentation. I will cover seven main sections: introduction and motivation, backgrounds, concepts, and FairNet framework, theoretical analysis, experimental results, discussion and analysis, and finally the conclusion. Let me start by explaining the fairness problem in machine learning. Machine learning models often exhibit bias against minority groups. This bias stems from imbalanced training data. This is critical in high-stakes domains such as hiring decisions, loan approvals, criminal justice, and healthcare. Fairness means ensuring equitable performance across different sensitive groups, for example, gender, race, or age. We measure this using metrics like worst group accuracy, which is the performance on the worst performing group, and equalized odds difference, which measure disparity in true and false positive rates. Existing debiasing methods have several limitations. First, there is a performance fairness trade-off. Most methods sacrifice overall accuracy to improve fairness, which is unacceptable in many real-world applications. Second, they use static correction strategies. They apply the same correction to all instances and ignore instance-level variations in bias. Third, they have data sparsity issues. They struggle with minority group underfitting because limited training samples lead to poor generalization. Fourth, they have suboptimal use of sensitive attributes. They either require complete attribute labeling or ignore sensitive attribute entirely. This brings us to the research motivation. The central question is, can we achieve fairness correction without sacrificing performance through dynamic instance-level adjustment? The desired properties are maintain overall accuracy, enable dynamic instance-level correction, handle partial or missing attributes, and address minority group underfitting. FairNet provides a solution through conditional LoRA activation, a contrastive learning approach, flexible attribute handling, and theoretical guarantees. Now let me introduce some background concepts. First is low rank adaptation, or LoRA. LoRA is a parameter-efficient fine-tuning method. It adds low-rank matrices to a frozen map model. The update is W primes time equals W0 plus delta W, which equals W0 plus B times A. Here, W0 is the frozen pre-trained weight, B is in R to the D times R, A is in R to the R times K, and R is much less than minimum of D and K, meaning low rank. The advantages are it reduces trainable parameters significantly, enable fast adaptation to new tasks, and preserve pre-trained knowledge. The concept is from Hu's paper, LoRA Low-Rank Adaptation of Large Language Models at ICLR 2022. Next, let me explain the fairness matrices. Demographic parity means the probability of predicting y equals 1 given attribute A equals A small a should equal the probability given A equals small a prime for all groups. Equalized odds means the probability of predicted y equals 1 given true y equals small y and A equals small a should equals the probability given y equals y and a equals small a prime for all small y and all groups. Equal opportunity means the probability of predicting y equals to 1 given 1 y equals 1 and a equals to small a should equals the probability given y equals 1 and a equals small a prime for all groups. In the notation, the big Y is the the capital Y is the true label. Predictive capital Y is the predicted label, and capital A is the sensitive attribute such as gender or race. EOD is equalized odd difference, which measures disparity. The third background concept is contrastive learning. The core idea is to learn representations by contrasting positive and negative pairs. This pulls similar samples together in embedding space and pushes the similar samples apart. The standard contrastive loss is negative log of exponential of similarity of zi and zj plus divided by tau divided by the sum over k of exponential of similarity of zi and zk divided by tau. Here, S is a similarity function. For example, cosine similarity. Tau is the temperature parameters. Zj plus is the positive pair, meaning same class but different group. And the small zk represent all samples in the batch. In FairNet, this is used to align representations across sensitive groups within the same class. Now let me present the FairNet framework. As you can see in the architecture diagram, FairNet has three key components. First is the bias detector, denoted D5 superscript I. It identifies instances likely from minority groups. It is a lightweight network at layer I. It outputs a risk score P S subscript I of x in the range of 0 to 1. Second is the conditional is the what is conditional LoRA. It is activated only for detected biased instances. The low rank adaptation is Wj plus indicator function of P as subscript I of x greater than tau times bjaj. This preserves performance on unbiased instances. And the third is the contrastive loss. Um, it minimizes intra-class disparities across groups, addresses minority group underfitting, and learns group invariant features. So let me explain the first component in detail. The bias detector. Its purpose is to identify instances where the model prediction is likely biased. The design is a lightweight classifier on top of intermediate representations. It takes h superscript I of x as input at layer I. It outputs a risk score P as superscript of x in 0 to 1. A threshold tau determines activation. The key insight is that not all instances are equally biased. Selective correction is more efficient and preserves performance on unbiased instances. The training loss is binary cross entropy of D5 superscript I of h superscript I of x and s, where s is in 0 or 1 indicates whether the instance is from the minority group. Conditional LoRA. The second component is conditional LoRA. The conditional activation mechanism is Wj prime equals Wj plus indicator function of Ps superscript I of x greater than tau times Bjaj. The inference process has 4 steps. First, compute intermediate representation h superscript I of x. Second, bias detectors evaluate and produce risk scores. Third, identify LoRa modules to activate based on threshold tau. Fourth, perform forward pass with FairNet enhanced model. The benefits are it preserves performance on unbiased instances, provides targeted corrections only where needed, is parameter efficient through LoRa, and has no degradation of base model capabilities. The third component is the novel contrastive conditional LoRa loss. This addresses minority group underfitting. The combined objective is L total equals LCE plus lambda com here, uh, lambda contrastive times L contrastive plus lambda detector times L detector. For the contrastive loss for fairness for each class C and instance Xi from group S, positive pairs on same class but different group, and negative pairs are different class. The goal is to align representations across groups within the same class. The effect is it encourages consistent representations within the same class, reduces group-specific feature reliance, and addresses data disparity through cross-group learning. The training process has two stages. Stage 1 is train bias detector. First, use the pre-trained base model. Second, le label instances based on sensitive attributes. Third, train the lightweight detector to predict group membership. Fourth, optimize using binary cross entropy. Stage 2 is train conditional LoRa. First, freeze the base model and bias detector. Second, initialize low rank matrices Bj and Aj. Third, for each batch, get bias predictions from detector, conditionally activate LoRa modules, compute classification loss plus contrastive loss, and update only LoRa parameters. The key point is the base model remains frozen throughout. Only LoRa parameters are trained. FairNet flexibly handles three scenarios. First is complete attribute code FairNet 4. All training samples have sensitive attributes labels. These uses standard training with full supervision. This achieves the best performance as shown in the experiment. Second is partial attribute called FairNet partial. Only some samples have attribute labels. It uses labeled samples for detector training and propagate bias predictions to unlabeled samples. Third is no attribute called FairNet unlabeled. No sensitive attribute labels are available. It uses auxiliary methods to infer attribute. It still achieves fairness improvement. The flexibility advantage is, unlike prior methods, FairNet does not require complete sensitive attribute labels. Now let me discuss the theoretical analysis. The main theory states under moderate quality of bias detector, FairNet can enhance worst group performance and maintain or improve overall performance. The key assumptions are: first, the bias detector has reasonable TPR or true positive rate and low FPR or false positive rate. Second, LoRa correction improves accuracy on minority group instances. Third, correction doesn't harm majority group instances. The intuition is selective correction avoids overcorrection. Minority groups benefit more from targeted adjustments. Base model performance is preserved on unbiased instances, and the net effect is improved worst group accuracy without overall degradation. Why does FairNet maintain performance? First, selective activation. Only about 10 to 13% of instances trigger LoRa correction. The majority of instances use the original base model. There is no interference with well-performing path. Second, low rank adaptation. There is minimum parameter overhead. It makes small targeted adjustments to representations. It preserves pre-trained knowledge. Third, contrastive learning. It improves minority group representations. It learns from the majority group through cross-group learning. It addresses data disparity without additional data. The result is fairness improvement without performance degradation. Now let me present the experimental result. The datasets are celeb A for facial attribute with gender bias. The task is to predict blonde hair attribute. The sensitive attribute is gender. There is a known spurious co correlation that blonde approximately equals female. Multi-NLI for natural language inference. The task is textual entailment classification. There is bias from lexical shortcut hate explain. For hate speech detection, it has multi-attributes, race and gender. It tests intersectional bias mitigation. The evaluation metrics are ACC for overall accuracy, WGA for worst group accuracy, which is the primary fairness metric, and EOD for equalized odds difference, where lower is better. Here are the main results on celeb A and multi-NLI. Let me highlight the key findings. For the scenario with no access to sensitive attributes, FairNet on label achieved 96% accuracy, 82% worst group accuracy, and 7% equalized odds difference on celeb A. It is the best in its category. For partial access, Fairness Partial achieved 96% accuracy on celeb A and 83% on multi-NLI, which is the highest accuracy. For full access, FairNet 4 achieved 96 accuracy, 88 worst group accuracy, and 4 equalized odds difference on celeb A. On multi-NLI, it achieved 83% accuracy, 79% worst group accuracy, and 5% equalized odds difference. These are state-of-the-art across all matrices. The key observation is FairNet 4 achieves the best performance across all metrics. It maintains the highest accuracy while significantly improving fairness. Even FairNet on label with no attributes outperforms many supervised methods. Let me analyze the results for the three scenarios. First, no access to sensitive attributes with FairNet on label. On celeb A, it achieved 96% accuracy, 82% worst group accuracy, and 7% equalized odds difference. It is the best in its category and matches ERM accuracy while improving fairness. Second, partial access with FairNet partial. On celeb A, it achieved 96% accuracy, 87% worst group accuracy, and 6% equalized odds difference. This is the highest accuracy in its category. It outperforms DFR and Zebra on both datasets. Third, full access with Fairness 4. On celeb A, it achieved 96% accuracy, 88% worst group accuracy, and 4% equalized odds difference. On multi-NLI, it achieved 3% accuracy, 79% word group accuracy, and then 5% equalized odds difference. This is the state of the art across all metrics. It is the only method achieving both high accuracy and fairness. The critical finding is FairNet improves fairness metrics while maintaining or exceeding baseline accuracy. Now let me show the intersectional bias results on Hate-X plane. FairNet used a progressive debiasing strategy, first target racial bias, then gender bias. Looking at the table, for disparate base, the baseline ERM has 26.5% equalized odds difference for race. After applying FairNet for African American group, it improves to 24.4%. After also applying FairNet for female group, it further improves to 23%. For gender, the equalized odds difference improves from 11.3% to 7.4%. For birth base, the results are even better. Racial equalized odds difference improves from 20.1% to 11.2% to 9.8%. Gender equalized odds difference improves from 12.9% to 8.2%. The key findings are progressive debiasing successfully reduces both racial and gender bias. Accuracy is maintained or improved throughout. This demonstrates modularity. FairNet can target multiple attributes sequentially. Okay, so now I'll show the ablation study results. This evaluates individual components. Looking at the table, FairNet partial achieved 95.9% accuracy and 86.5% word group accuracy and 5.6% equalized odds difference on setup A. Without the detector, accuracy drops to 94.1%, which is at 1.8% decrease. Without contrastive loss, word group accuracy drops to 81.2%, which is a 5.3% decrease, and equalized odds of the difference worsens to 8.5%. On multi-NLI, without the detector, accuracy drops from 82.6% to 81%, a 1.6 decrease. Without contrastive loss, word group accuracy drops from 76.5% to 70.1%, a 6.4% decrease. Sorry. The analysis shows without the detector, accuracy drops significantly, showing the detector preserves accuracy. Without contrastive loss, word group accuracy and the equalized odds difference worsen significantly. The contrastive loss is critical for fairness improvement. The bias detector is critical for maintaining overall accuracy. Both components work synergistically. So let me discuss why FairNet works. First, selective correction. It avoids overcorrection on unbiased instances and preserves the base model's strong performance. It provides focused improvement where needed most. Second, contrastive learning. It addresses data disparity through cross-group learning. It learns group invariant features within classes. It reduces reliance on spurious correlations. Third, parameter efficiency. Low-rank adaptation minimizes parameter overhead. These enables faster training and deployment. It is easy to integrate with existing models. Fourth, flexible attribute handling. It works with partial or no sensitive attribute. This is more practical for real-world deployment. Let me summarize the advantage of FairNet. The technical advantages are no performance degradation, instance level adaptation, theoretical guarantees, and parameter efficiency and modular design. The practical advantages are easy integration, flexible attribute requirements, scalability to large models, and domain agnostic application. The empirical evidence shows consistent improvements across vision on setup A, NLP on multi-NLI, and hate speech on hate explain. It achieves the best words group performance and maintains or improved accuracy. It works with all attribute scenarios. The uniqueness is it is the only method achieving both high accuracy and fairness simultaneously. Now, let me discuss the limitations and challenges. First, detector dependency. Performance relies on biased detector quality. A poor detector can limit improvement. The mitigation is careful detector training and validation. Second, computational overhead. This is an additional forward pass through the detector. LoRa parameters need to be trained and stored. However, it is still more efficient than for fine-tuning. Third, hyperparameter sensitivity. There is loss weight balancing for lambda contrastive and lambda detector. There is LoRa rank selection and threshold tau setting. Fourth, sequential multi-attribute handling. The current approach is progressive debiasing. Future work should address simultaneous multi-attribute fairness. Let me compare FairNet with related work. Compared to Group DRO, FairNet maintains accuracy and provides instance level correction. Compared to reweighting, FairNet has no performance loss and enables dynamic adaptation. Compared to adversarial debiasing, FairNet has a better accuracy fairness trade-off. Compared to fair mix-up, FairNet works with partial attribute and has better performance. This number contributions are: first, it is the first to achieve fairness without performance loss. Second, it provides instance level dynamic correction via conditional LoRa. Third, it uses contrastive learning for minority group improvement. Fourth, it has flexible handling of sensitive attribute availability. Fifth, it provides theoretical guarantees on performance preservation. And let me discuss the societal impact and ethics. The positive impacts are: it reduces algorithmic discrimination, promotes equitable AI systems, increases trust in ML applications, and addresses legal and ethical concerns. The potential concerns are privacy because it uses sensitive attributes, misuse because it could be used to superficially mask biases, fairness definition because different notions may conflict. The recommendations are transparent deployment with clear documentation, regular auditing and monitoring, stakeholder involvement and fairness definition, and considering multi-fairness metrics. Let me summarize the contributions. FairNet introduced four main things. First, a novel framework with dynamic instant level fairness correction, a conditional LoRa activation mechanism, and it is the first method achieving fairness without performance loss. Second, technical innovations include contrastive condition LoRa laws, a bias detector for selective correction, and flexible handling of sensitive attributes. Third, theoretical insights with performance preservation and guarantees, and works group improvement analysis. Fourth, empirical validation with state-of-the-art results across vision and NLP comprehensive evaluation on the various scenarios. So here are the key takeaways. The main message is fairness and performance are not fundamentally at odds. With a proper instance level adaptation, we can achieve both. The critical insights are: first, selective is better. Not all instances need correction. Second, dynamic adaptation. Instant level decisions outperform global strategies. Third, cross group learning. The contrastive approach addresses data disparity. Fourth, practical flexibility. The framework works with partial or no sensitive attribute. Fifth, theoretical foundation. The guarantee provides confidence or deployment. For deployment, the impact is FairNet provides a practical, theoretically grounded solution for deploying fairer ML system without sacrificing performance. Let me discuss the significance for security and privacy for machine learning. The relevance to this course is that fairness as security bias models are vulnerable to exploitation. Privacy considerations is handling sensitive attributes securely. Robustness fairness models are often more robust to adversarial attack. Ethical AI fairness, the fundamental to trustworthy ML systems. The connections to course topics are first, adversarial ML bias is a form of vulnerability. Second, privacy preserving ML in handling sensitive attributes. Third, model auditing for detecting and correction biases. Fourth, trustworthy AI where fairness is a trust requirement. The key insight is fairness is not just an ethical concern, but a security and robustness requirement for production ML system. Let me discuss future directions. The potential extensions are first, simultaneous multi-attribute fairness, handle multiple sensitive attributes jointly and address intersectionality more effectively. Second, advanced bias detection with uncertainty-aware detection and self-supervised bias discovery. Third, scaling to large models applying to LLMs at GPT scale with distributed training strategies. Fourth, domain-specific adaptations for healthcare, finance, and criminal justice with tailored fairness metrics per domain. Here are the main references. The main paper is Zhou, Liu, and Jiang, 2025, FairNet Dynamic Fairness Correction with a Performance Loss via Contrastive Conditional LoRa at NeurIPS 2025. And the code is also available at GitHub. The key references are WHO LoRa, low rank adaptation of large language models at ICLR 2020. Distri- Distributionally robust neural networks at ICLR 2016, Equality of Opportunity in Supervised Learning at NeurIPS. Thank you for attention, and I am now open for question and discussion. Please leave a comment below, and you can find the paper at this GitHub or just Google it online. Thank you.